The study of astronomy is highly visual. Whether in a textbook or the news, you've likely seen incredible pictures of the moon, stars, planets, galaxies, and more. The most recognizable of these images are captured by optical telescopes, which capture what the naked eye can see. However, other types of telescopes can produce images as well, including radio, infrared, ultraviolet, X-ray, and gamma-ray telescopes. Radio astronomy images, for example, are produced by amplifying and converting weak radio signals collected from space to numerical data. Computers then analyze the data to create images of celestial objects. What kinds of objects in space emit radio signals? How do radio telescopes detect them? And what do scientists learn from these signals? Stick around to find out on this episode of Beyond the Breakthrough, where we break down the latest developments in science and technology with help from the experts behind them. I'm Kelsey Underwood, your host and digital communications specialist at AUI. Before we get started, please note the Green Bank Observatory and the National Radio Astronomy Observatory are facilities of the U.S. National Science Foundation, operated under cooperative agreement with Associated Universities Incorporated. The opinions expressed in this podcast episode do not necessarily represent those of the NSF, and the implementation of any radar system on these facilities would be subject to NSF review and approval. Now let's dive in.
In the Air Force world, there are antennas. In Green Bank, there are telescopes, but we're using a lot of the same technology.
That's Will Armentrout, a scientist for the U.S. National Science Foundation's Green Bank Observatory. Will has worked at the Green Bank Observatory since 2018, starting as a postdoc researcher and now researching galaxy formation and structure as a scientist. In addition, he serves as a space operator in the U.S. Air Force. Whether at the Green Bank Observatory or on an Air Force base, Will works with data from parabolic antennas regularly. Optical telescopes and radio telescopes both detect waves on the electromagnetic spectrum. In fact, all the types of telescopes I mentioned earlier do. Each type of telescope focuses on a particular kind of electromagnetic wave. Optical telescopes gather and focus visible light. You may know the visible light spectrum as the acronym ROY-G-BIV: red, orange, yellow, green, blue, indigo, and violet. Radio telescopes, on the other hand, detect and magnify radio waves. Radio waves are much longer than visible light waves, which cause them to be invisible to the naked eye. Will uses sine waves, which you may recall from high school trigonometry, to explain.
So optical light, if you think about a sine wave, the distance between the two peaks is about, let's say, 700 nanometers. So 700 times 10 to the minus 9 meters. For radio waves, it can go anywhere from millimeters up to meters between the two peaks of that sine wave. So the one famous line that we look at is the 21 centimeter hydrogen line. And that 21 centimeter hydrogen line would have a distance of 21 centimeters between the two peaks of that sine wave. So this is one big reason that your eyes can't see radio waves, right? Because the waves really can't fit in your eye between those two peaks.
For reference, a meter is just over 3 feet. A millimeter is 1/1000th of a meter, and a nanometer is 1/1,000,000th of a millimeter. Optical astronomy has been around since the 17th century, with Galileo Galilei often credited as the inventor of the optical telescope. However, radio astronomy was discovered much more recently. The first known radio astronomy observation was completed in 1933 by Carl G. Jansky, a young engineer at Bell Telephone Laboratories. Jansky was tasked with identifying the source of static interference during transatlantic radio communications. He ended up detecting radio waves emitting from the center of the Milky Way galaxy, which he initially thought was an interference.
Radio astronomy is sort of the new kid on the block. People have been looking up at stars with optical light and telescopes for hundreds of years, but radio astronomy is only about 100 years old. It really grew up after World War II, when countries had all of this radar equipment and didn't need to use it anymore for war purposes. So there were governments around the world that had that strong expertise, the United States, Australia, Germany, Russia, and they tried to turn that expertise into an astronomy field in looking at these radio wavelengths. So radio astronomy is more similar to like electrical engineering than it is to maybe classical optical astronomy.
The Green Bank Observatory, often referred to as GBO, was initially founded as part of the U.S. National Science Foundation National Radio Astronomy Observatory in 1956, about a decade after World War II ended. Today at GBO, 8 radio telescopes with dishes spanning as wide as 328 feet detect radio waves emitted by distant space objects such as stars, planets, galaxies, and black holes, just to name a few. So, how do radio astronomers know which of these telescopes to use?
In order for a telescope to detect a radio wave, the size of the instrument kind of scales with the wavelength. So if you want to detect a 21 centimeter wave, you have to have an instrument that is on the same scale about as that wavelength. And so if you look at some of our telescopes in Green Bank or at the Very Large Array or at ALMA, the longer the wavelength of light that the telescope is looking at, the larger the instrument is. So we have these things called feed horns, and the bigger the feed horn, the longer the wavelength of light that it's looking at.
One of the simplest visual references for a radio telescope is the satellite antenna emoji. While many details are of course missing from this illustration, it provides a good mental picture during an explanation of how these complex instruments work. Each radio telescope has numerous components. However, the key parts when it comes to detecting radio waves are the dish, subreflector, feed horn, and receivers. The large metal dish works as a reflector, bouncing incoming radio waves up to the subreflector, which is held by 4 arms extending from the dish and meeting centrally above it. From the subreflector, the radio waves enter the feed horn, which guides them into receivers. Cooled to 16 degrees above absolute zero, or negative 457 degrees Fahrenheit, to reduce noise generated by electronics, receivers split, amplify, shape, and detect the extremely low power signals that entered the feed horn. Will analogizes to further illustrate how feed horns function using buckets and rain.
If you have a tiny little bucket, you're not going to collect much rain. If you have a gigantic barrel, you're going to collect probably a lot of rain. In this metaphor, the rain are the photons that are coming in that you're then collecting with the receiver. So once you've collected that light into that tiny little point on the receiver, then we turn that light, those electromagnetic waves, those radio waves, into electricity, and we measure the intensity of those little light rays at different frequencies.
Let's take a moment to clarify a common misconception about radio astronomy. While radio commonly brings music and talk shows to mind, radio waves themselves don't create the audio produced by musical radios, but by the receiver circuitry that converts the radio waves into audible sound. In other words, radio waves can't make sound because they're a type of light wave rather than a sound wave. And while radio astronomers can't hear or directly see the space objects they're researching, they are able to identify them by analyzing the collected radio waves. To do so, astronomers match each radio wavelength to its coordinating chemical element. Sometimes an element's unique frequency is referred to as its spectral fingerprint.
You can see how much hydrogen there is, how much carbon monoxide, how much cyanide, right? And since we are studying the makeup of stars and planets and nebulae and things back to the beginning of time, pulsars, things like this, looking at how intense radiation is from all of those different atomic and molecular species can tell us a lot about the environment surrounding these astronomical objects.
The intensity of radio wave transmission, or radiation, is evaluated by examining radio images, or radio maps, which visually represent the concentration of radio waves within a studied area of space. Often, the brighter an area of a radio image, the more of a material that's present. So, which elements exist in space, and how did they get there?
In the beginning, there was hydrogen and a little bit of helium and even less lithium. So after the Big Bang, those were the elements that were around. And the first set of stars formed from only those three elements. So the first stars that were ever in existence at the beginning only had hydrogen, helium, and lithium in them. Now, obviously, now we have more elements than that. We are made of other things other than hydrogen, helium, and lithium. But all of the things that are making up our bodies and the Earth and the other planets in the solar system are the product of star formation. So those first stars were made up of those three elements, hydrogen, helium, and lithium. And through their star formation, through their stellar lifetime and supernova at the end, they produced other elements that then were dispersed across space. And then those elements were used in the next generation of stars.
What's a supernova, you may be asking?
After high mass stars go kaput, go supernova, they throw all of these elements out into space, and then those are used to form new stars, new planets, and other nebulae around the Milky Way galaxy and beyond.
Once these elements are released from their star parents, they begin interacting and sometimes form new space objects such as stars and planets, including Earth. In addition to planets and stars, what other space objects do astronomers at the Green Bank Observatory study?
I've mostly talked about star formation because that's what I do. But our telescopes are used for a ton of other programs. And one of those is on what we call transient sources. So we study things called pulsars, which are these rapidly spinning stars that are beaming out radio energy at their poles. And every time they spin around, one of those poles points towards us, and our telescopes can pick up a blip. So imagine like beep, 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 beep. These pulsars spin very regularly, and we can use them to try to understand better general relativity and some of Einstein's theories about how the universe works beyond some of our classical physics ideas. We also look for these things called fast radio bursts, which are these random bursts of radio energy coming from seemingly random parts of the universe. And we don't really understand right now where they're coming from. They were only discovered about 10 years ago, but they're kind of one of the new mysteries in astronomy. So we're trying to understand better what might be causing those types of things.
And then there's radar. Radio astronomy involves passively observing radio waves from space, whereas radar involves actively sending and receiving the same radio waves to and from space. Changes between the transmitted and received waves tell scientists about the space objects in the targeted area. Will discusses radar in full length during an upcoming episode of Beyond the Breakthrough, so stay tuned for it this summer.
So we talked about how radio astronomy kind of grew up from radar technology, but we still use it as part of our toolkit. And we have some of the best images you can get of outer space from the ground from this radar technology. So the Green Bank telescope, for instance, has made the best radar image of the moon, the best ground-based image of the moon with our prototype radar system.
Will is referring to the Tycho crater radar image captured by the prototype radar technology on the Green Bank telescope in 2021 and made possible by the NRAO, GBO, and Raytheon Intelligence and Space. A link to the image is included in the show notes. In addition to planetary science, radar is also used for defense.
So whenever we think about what radar is used for in astronomy, usually the first thing people think of are asteroids. So if an asteroid would be coming towards the Earth, we are able to characterize its orbit, tell what its motion is, if it might be on an impact trajectory with the Earth. And if we ever have something like the dinosaurs had that came and impacted the Earth, with our radar technology, we would be able to tell well in advance that it was coming, and then hopefully put something together to try to push the asteroid away or do something else, so that we don't go the way of the dinosaurs.
Just how far into space can radio telescopes detect these example space objects and many others? Will says they can be detected as far as billions of light years away. And without the discovery of radio astronomy and continuous advancement, none of this exploration would be possible. Throughout their history, AUI and the National Radio Astronomy Observatory and the National Science Foundation have invested in the development of radio astronomy by creating new technologies, building next-generation telescopes, and supporting future scientists and engineers.
It's sort of I think it's a really fun job to be an astronomer at an observatory, because you don't only have your research, you have the whole infrastructure of the observatory that you get to be a part of, and you get to help guide new instruments and new programs for the future of astronomy. So this is a great place for me, and I think you'll find the same story from a lot of the astronomers around Green Bank and the NRAO sites.
That wraps up our crash course on radio astronomy. Will, thanks for joining us, and thank you for your service as well. Will did an excellent job breaking down the basics of radio astronomy. However, we only have so much time in an episode. I highly encourage you to visit the National Radio Astronomy Observatory website at nrao.edu to delve deeper into topics that interested you today and to learn even more about radio astronomy, space objects, and NRAO observatories. Also, to learn more about Will's work specifically, visit his website, willarmentrout.com. As I mentioned before, Will be back for another episode about radar and its role in planetary defense later this summer. If you're enjoying the podcast and you would like to be notified about new Beyond the Breakthrough episodes and special segments, be sure to subscribe wherever you're listening and consider leaving us a review to let us know how you like the podcast. Also, follow AUI on Instagram at DiscoverAUI and Associated Universities, Inc. on Facebook and LinkedIn to stay updated on all the latest breakthroughs at AUI. Thanks for joining me today, and I will see you next time.